I'm going to talk to you about how static analysis tools love PureFP. So, just so we're all on the same basis, when I mean a static analysis tool, I mean a tool that looks at your code, doesn't execute it, and then does something. So a compiler is a static analysis tool, a type checker, code formatter, code optimizer, and linter. Those are all static analysis tools. There are more of those. And the one we're going to focus most on today is the one that we call linters. So they're tools that are going to look at your code and find ways to make it better or to find errors. And then they're the origin of mostly all the squiggly lines that you see in your editor, along with compilers. But some of the things that I'm going to talk about also make sense for other kinds of static analysis tools. So if you're more interested in those, then you can keep listening. So the reason why I want to do this talk is because I made a tool called Elm Review, which is a linter for the Elm language. And people seem to quite like it. I'm pretty happy with it. There are multiple reasons for that. One of the reasons for that is because it makes quite nice error messages, nicer error messages than just one-liners that you see in most editors or most linters out there. But also, it makes very nice reports in the sense that it doesn't report false positives as much as the other tools do. And some of that comes to the design of the tool, but over the years I've come to appreciate how much of that is actually due to the target language, which is Elm. So Elm is a pure functional language, meaning that it doesn't have any mutability. Functions don't have side effects. They can't mutate things. They can't make HTTP calls like willy-nilly. It is a compiled language, and it is statically type-checked. So this is all I'm going to say about Elm, mostly. If you want to know more about that, there's several Elm talks after this. But we're going to focus on these 3 points, and we're going to see how they make analysis easier. So I first want to emphasize how developers dislike linters. They're a tool that they usually don't trust. And the main reason for that, except for the fact that all errors are just one-liners, that doesn't give a lot of context, is because developers don't like false positives. I think no one here likes those. So when you're working on some code, at some point the linter is going to tell you, hey, there's an error here on this line in this file. And you're going to be like, OK, I'll take a look at it. No, that actually looks OK. That's a false positive. Like, the code is correct. There's no problem. It should be like that. So thank you for the reports. But I'm going to add a disable comment. And therefore, you're not going to bother me with this issue anymore. And the linter is going to do that again, because it's going to find more errors. You're going to look at it again, and sometimes it will be correct, sometimes it will not. When it will not, you add a disable comment again. And the more that you do this, the more you get into a rhythm, a groove, to add more of those. And at some point, your code is going to be filled with these disable comments, which I think make your code worse. And this is a really bad state to get into, because this basically means that you stop trusting the tool. Some people actually stop using linters altogether in some parts of our industry, which is super surprising to me, but research has shown that, because they report way too many false positives. And when you have like a linter report thousands of errors and 20–30% of them are false positives, well, that's a huge time waster. And I can understand why you would be very frustrated with that. So when we talk about a linter or a compiler, a false positive is causing you to be unnecessarily blocked. You need to do something, change your code, add a disable comment, in order to move on. You also have false negatives. That is when the tool doesn't report an issue when it should. That's a lot less annoying than a false positive, because it doesn't block you and you don't notice it. But that is a missed problem. And in some cases, it can be actually worse. Because if you configured your tool to report instances where your code would crash, well, you want to know about those. And if you don't know, you're going to feel safe when you shouldn't. If we talk about a code optimizer, a false positive would be the tool optimizing some code when it shouldn't. So that's going to potentially change the behavior, that's going to cause a crash, and that's going to be very hard to debug. And a false negative would be the optimizer doesn't apply an optimization when it should have. And that's going to be hard to notice. You're mostly going to notice it by saying like, this is running slower than I expected. And good luck finding out why that was as well. So all of these false positives and false negatives, they're bad, and we want to get rid of those. So why do we have them? Well, what I've come to the conclusion to is that it's basically caused because of missing information. If your tool had perfect knowledge of your code, knowledge behind the domain, what is going on in your developer's head, it would never report a false positive, and it would never miss something to report. But unfortunately, we have missing information. Like, programming languages are hard to analyze. The tool sometimes doesn't give all the information to the rules that it uses. So we do have missing information. And when we have missing information, we're making presumptions. And a presumption is the acceptance of something as true on the basis of probability. So like, I don't know whether this is true, but it's very likely going to be true because it is in 99% of the cases, or something like that. Or that's going to give the best results in most cases. And when these presumptions turn out to be wrong, that's when you have a false positive or a false negative. So let's take an example. So this is JavaScript code. JavaScript has a static analysis tool called ESLint, which is a good tool. I'm going to talk about it a few times. It has a few problems, mostly because it has a problematic target language, which is JavaScript, but it's a good tool. So this tool has a rule called array callback return, which basically reports when you use the map method on an array, and that you're passing it a function that doesn't have a return statement, meaning that this doesn't return something, which is a problem when you want to map an array. You want to map every element to something, not to undefined in this case. So what this rule does is it's looking for a map method call. So anything that looks like something.map and that is being called, and you pass it a function, well, that's going to be array.map, right? And that could be wrong, because, for instance, in this case, my array is not really an array. It is something that looks like it, and that happens to have a map function, which I don't know what it does. Maybe it creates a map, which would be a good name, I'd say. So here, we made an incorrect presumption. Because we don't know what the type of array is, because JavaScript doesn't have type information. TypeScript kind of helps with that. But since we don't have that information, we're going to have to make presumptions, and in 99% of the cases, this is going to be true, this is going to be an array, but not always. So what can we do instead? Like, what we did is, what this rule does, it reports issues when the thing looks like an array. But what you can do also is to report when the rule knows it's an array. Like, it can figure out more information based on the context. If it knows it's an array, then it reports an error. And if it doesn't know, it doesn't report anything. And that gets rid of all the false positives. But that gives us false negatives. So when you have this missing information, when you're making presumptions, you're going to have either false negatives or positives. You're going to be able to lean towards one or the other, but you're going to have to choose which problem to go for. Usually, you want to go for false negatives, because unless it's a critical issue. So presumptions are a useful and necessary tool. but they can create problems when they turn out to be wrong. What we want instead is more information and guarantees about the code. Like we want to be sure that something works as it is expected. So what guarantees can we have when we analyze source code? And that's what we're going to look at right now. So this is code from your favorite language. This is both JavaScript code, this is both Haskell code. It is obviously incorrect code, but it is something that you could find in a .js or .hs file. And if that happens, well, if you run your linter will have to analyze this code. And where do you start? Like, kind of hard because like there's so much wrong going here. Thankfully, linters and most static analysis tools, they don't look at code like this. What they do, they have a parsing phase where they parse this code into what we call an abstract syntax tree, or an AST for short. So an abstract syntax tree is a data structure that represents the structure of your code, and that is shaped like a tree. So if we have the expression a plus b divided by 2, that could be represented with an AST like this, where you have a binary expression using slash, on the right side an integer 2, on the left side a parenthesized expression with a binary expression with references to both a and b. And the nice thing with the fact that we are doing this parsing phase is that if the parsing phase doesn't succeed, well, it's going to stop the analysis. Like, it's not going to run all the rules or the rest of the analysis. It's going to tell you, the user, hey, I've found a syntax error here. Can you please fix it before I continue with the analysis? And that means that when you're working on a rule, you can have the guarantee that the analyzed code is syntactically correct. You don't have to worry about code being like not correct language code. This is true in theory. Potentially you can have bugs in your parser, but at least in theory, it is true. This is obviously not true if you're working for linter in an IDE, because that one aims to work with code that is still work in progress. So those guys working on that have it tough. Good luck on them. So a nice thing that you can do with ASTs is you can pattern match on them. And then you go through them, you pattern match, and based on what you find, you report errors. And that is basically what a linting rule is. So if we have a rule that wants to report divisions by 0, which is a bad thing to do, what you could do is write a rule that goes through the AST and says, if I see a binary expression using slash, the division operator, where on the right side there's an integer 0, then report a problem. So this is a very trivial example, a very simple one, but it works. And that is basically a very simple linting rule. So now let's look at some very complex code. So let's say, for instance, we wanted to know the value of this expression. Well, it's not too hard. Like, we have some variable, we look it up in the context, and then we add +1. But here we're making a potential presumption, which is that this variable has been defined somewhere. That might not be true. And we don't want to, every time we analyze code, to have to worry about, like, potentially some variable does not exist. Like, handle the case where it does not exist. So how can we get this guarantee? And that is what compilers are for. At least that's one of the things that they tend to do. So a compiler is going to check for a lot of semantic errors. It's going to check for undefined references. It's going to check for imports to unknown modules, duplicate declarations, calling a function with too few or too many arguments, etc. Some languages or some compilers will do more, some others will do less. And because you have all of these checks done by the compiler, you have a lot more guarantees that the code works as you expect. You have a lot less surprises. In order to do this, you do have to have the compiler be run before the analysis. There's several ways to do it. Elm review basically tells the users, don't run the analysis before you have compiled, before you know the code compiles. It's not great, but it works. Some other linters, they actually invoke the compiler to get things like type information. So if the compilation fails, they can abort the analysis. And some actually integrate as a plugin to the compiler, and therefore the analysis will not even be run if the program doesn't compile. But what to do if your language doesn't have a compiler? Like if you're working with JavaScript, Python, or Ruby, or languages like that. Well, what I usually see is people write linter rules. Lots of them, really lots of them. So basically everything that can be a semantic error, everything that a compiler already checks for, though you would have a linter rule for that. One for checking undefined references, one for duplicate declarations, and so on and so on. And if you want your rules to be able to depend on those guarantees, all of these rules will have to be enabled by default. So they have to come with the tool, and they have to be enabled, because otherwise, like potentially, some rule is depending on that guarantee, and it doesn't have it. But it doesn't work as well as with the compiler, because these issues can potentially be ignored using a disable comment. And also, you can have the issue where one rule, where all the rules are at the same level, like conceptually, they're all run at the same time. And one is depending on the fact that there's this guarantee, and because it doesn't have it yet, it's going to have a false positive. And at the same time, there's the rule that enforces the guarantee that is being run. So one kind of has to be run before the other. So how many rules am I talking about? So I had some little fun going through all the ESLint rules, the ones that come with the tool, not the thousands that come from the NPM package ecosystem. And I wanted to see which ones apply to Elm and which ones don't make sense. And I found that 92% of all the rules that are enabled by default don't make sense for Elm. And 86% of all the other ones, all of them, don't make sense. What do I mean with they don't make sense? I mean, the compiler already checks for those issues, so you don't have to do another linting rule to reinforce that fact. Or some features are for JavaScript, and Elm doesn't have those features, so kind of by language design. So those don't make sense in Elm. The line can get kind of blurry as well, but I try to be on the side of ESLint, so this is a very conservative number. And yeah, Elm's language design also makes it so that a lot of these problems can't happen just by syntax. So there are a lot of rules in ESLint, like at least 263, but thousands more in packages. And it's very hard to configure all those rules, to know which ones to pick, to know which ones not to pick. So basically, you have three options. One, you don't use the tool. Two, you have someone on your team or multiple people on the team that take care of configuring this tool. That person used to be me on multiple of my companies. It's a fun job, but yeah. And the third option is to just use someone else's configuration. So in the JavaScript ecosystem, you've got a few packages or a few configurations that are downloaded multiple million times per week. So this is a quite often chosen solution. And those work well because some very smart people at large companies have defined, like, we want these rules, we want them configured like this, we don't want these rules. So they're quality configurations. But they work for their team, their projects, their coding style. And when you accept those configurations, that might not be true. You don't have the same project, you don't have the same code style. So you're going to enable rules that you don't agree with. And that can very much lead to frustration, because the line between a false positive and a rule or an area that you don't agree with is very, very thin. It's going to lead to the same disable comments, going to lead to the same frustration. At some point, you're finally going to decide, well, we should probably disable that rule. But that usually happens way too late in the frustration phase. So now let's look at some code we know again. So we want to compute the value of some variable plus 1. So now, because we have a compiler, we know that some variable exists. We don't have to check for that again. But do we know whether this is something that you can add 1 to? Because potentially some variable is a string. Maybe it's a function. Maybe it's something else. And you don't want to add 1 to that. You don't want to have to check for that. Like, is this an integer? Maybe. So what do we use to have that guarantee? Well, that's what we use the static type checker for. They're usually part of the compiler, but not always. Like some languages like Elixir or Clojure are compiled languages, but they don't have a type checker. So you don't have these kinds of guarantee. And these tools are going to look for type mismatches or invalid operations on some values. And it's going to give you, again, more guarantees that you can depend on. And it's actually going to be able to allow you to do some nice shortcuts. So if you go to the array.map example, which, by the way, won't happen in Elm because you wouldn't have this rule in Elm because all functions in Elm return a value implicitly. So you wouldn't have to write this rule. So the way that you would write this function in Elm would be like this. So you have array.map, a function to explain how to map the item, and then the array to map onto. So one thing that we can see is that there's an explicit call to the target function. So we know that this is array.map. There's no ambiguity here, or it's very easy to figure out whether this is the one that we want to target. So we wouldn't have the same false positives that ESNs would have. I won't talk much about explicitness, but if your language is very explicit, that makes it much easier to analyze. So because array.map, we know that it's the array.map function that we want to target, and we know that its second argument is an array. Because we know that the code type checks, we're now guaranteed that this value is an array. And that means that even without invoking the compiler, even without getting information from the official source of truth, we know that this is an array. We don't have to compute it in a roundabout way. It's a very quick shortcut that you can make. So Elm Review actually doesn't have type information so far. But it's able to do very few false positives because of tricks like this or because we don't need it. So now let's talk about side effects. Rule authors, they don't like having to handle side effects. They don't want to analyze those. At least I don't, and I'm a rule author. So a side effect is when the function does anything else than just returning a value based on its inputs. So it's like mutating a variable or triggering a HTTP request, something like that. So to showcase that, let's look at what dependencies are in a function. So here, for instance, we see that both A and B, they reference arguments. That means that both A and B depend on arguments. The values of those depend on arguments. We see that C references A and B, so C depends on A and B. And the return value references C, so that depends on C. That's very easy. You can see it at a glance, and so does a static analysis tool. But let's look at the functions that we're invoking. So we see that func1 has a side effect. It's referencing and mutating a global variable. And we also see that func2 references that same variable, meaning that the return value of func2 depends on func1 implicitly. And that means that the value of B depends on func1 being called, which is not very explicit. And if we don't look at func3 or func4, well, maybe we have more of these hidden dependencies, maybe we don't. We don't know. So references, they indicate explicit dependencies on values or computations. Side effects, they create hidden dependencies on operations. So B doesn't depend on A, it depends on func1 being called, because func2 depends on func1. And this makes analysis much harder. Thankfully, we have a nice thing that is called functional programming, because functional programming is basically about programming without side effects, right? And when you don't have side effects to worry about, that makes analysis much easier, right? You would presume so, but that's not true, because when we do functional programming, we do have side effects. We have less of those, but we do have them. And it's only when you have a pure functional language that you have this as a guarantee, that you can start relying on that. If you do have the potential for side effects, then you have to analyze them, otherwise you risk false positives or negatives. So when you only have a language with, when your language only has pure functions, it doesn't have side effects, it doesn't have mutation, it opens up to new opportunities that would be so much harder to compute if you had them. And these checks are going to be very trivial compared to that. So for instance, we can move operations around. So here we have some function which defines a value that is very expensive to compute. And then based on whether we need to compute that function, the value, we use it, otherwise we return 0. So you can clearly see like there's a problem here because we compute something very expensive, and then in half of the cases we throw it away. So that's a bit wasteful. So let's look at the references, the dependencies. So we see that value references n, or the computation for value references n, so value depends on n. We see that the condition also depends on n, and we see that the then branch depends on value because it references it. And these are all the references that we see, all the dependencies that we see in this function. And that means that we can easily move it to inside the if branch. Like, these are all the checks that you would need to do. But if you had side effects, you wouldn't be able to do this without risking a false positive, or needing to analyze, need to compute an expensive computation. Because potentially, we have changed the order of these functions, and potentially one impacts the other, or one has a dependency on the other. And you can check for that, but that would be hard. And when I say hard, I mean you would need to write a lot of code to analyze that. It would take a lot of computing power, computing processing power, meaning your tool would run slower. And maybe at the end, you will still not be able to figure out whether these two functions have any, and whether they impact each other or not. But if we don't have any side effects, this is trivial. So you can do this for a lot of other things. For instance, if you have successive lists, .map functions, you can rearrange the operations to do less looping over the list. And code optimizers use these techniques a lot. But they can only do that if they know that it's not going to have a false positive. It's not going to be able to change behavior of the code. And if you don't know, well, you don't do it. We also have a lot of guarantees about pure functions, about the return value of pure functions. We know, for instance, that when a function's return value only depends on its inputs and constants, maybe. So that means that without even looking at the implementation of f, we know, and we don't know what the return value is, but without looking at it, we know that f of n will equal f of n. So we can simplify this to true. And we can simplify that even further to just 1. All these functions are returning the same value. And again, that would be a lot harder to do if you had side effects or mutations. And when you don't have side effects, dead code elimination is a breeze. It's like super nice. And I know it's something that the people who use Elm Review love really a lot about the tool. And it's just because it's so easy. So here we have a say hello function, which defines a variable that is never used. Hint, it's never used. And it returns hello plus a formatted name. So never used is never referenced. We could compute the dependencies again with the arrows, but that would just say that nothing depends on never used. Therefore, we could remove it. So let's remove it. But we can only remove the assignment, the to uppercase. We can't remove to uppercase because that might have side effects. So we can only remove the assignment to never used. But if we know that we don't have any side effects in our language, we can remove both the variable and the computation. And that is very easy to do. And this can create a domino effect. You remove one function call, and now we can look at, like, is to uppercase used anywhere? No. Oh, I'll just remove it. And in its implementation, was it calling functions? Okay. Are those used anywhere else anymore? No? Okay. Let's remove them as well. And then you go on and on like this, and at some point you might figure out, like, hey, actually this dependency is never used. We can remove it, because adding a dependency doesn't have a side effect. Oh, this module is never imported anymore. Just remove it, or remove the imports as well. And these are all trivial checks to do. So that's really nice. But if we were in a language with side effects, then you would stop this process at checking, reporting, hey, this variable never used is never used. Remove that one. So we could not start this domino effect. So when we introduced Elm Review at my company, at Humio, it wasn't as good as it is today at detecting unused code, but if I recall correctly, it removed about 5% of the entire code base in one swoop, and that was over several hundreds of files. And we felt super great about that, because that's 5% of the entire code base that we don't have to maintain anymore. But back when I was a JavaScript developer, if you were to come up to me saying, hey, I have a pull request, I removed 5% of the lines of code. I didn't change behavior at all, I swear. And it's over several hundreds of files. I would be like, no. Like, I have no clue of checking whether you've changed any behavior. It's going to be super hard for me to figure that out. But if you don't have any side effects in your language, it's trivial check upon trivial check upon trivial check. And that makes it very easy. And also you have a compiler that you can then, that will tell you, like, hey, you messed up somewhere. Like, you never call this function, but this function never exists anymore. So you do have some fallbacks or some tools that will help you figure out issues. This only works if your language doesn't have some troublesome features. So when I say troublesome, it's troublesome to people like me who do static analysis. So let's say we have an unused function. We see no reference to it anywhere in the code. So we want to remove it because it looks unused, right? But if you have in your language a way to dynamically reference that function, then potentially you now broke the code. So you will either not report this function as unused, or you will report it, but with a potential for a false positive, meaning you will see a disable comment appearing next to it quite soon. If you have arbitrary code execution, again, you can't tell anything. And if you change your code after the analysis, like if you inject a call to unused function after the analysis has run, then again, false positive. So some ecosystems like to do this. If you have macros in your language and that the linter doesn't understand, then you're going to have these problems as well. I think. I haven't used macros too much, but I So you have other features like this that can be troublesome for static analysis. Usually they relate to dynamic things. And I'm not saying that these are bad. These are useful features. But it's a trade-off, because if you don't have these, you can have some very nice code guarantees about your code. In Elm, if we know if the analysis has run and the compiler is happy, and we see that a function is still in the code, we know that it is being used somewhere. If we see a variable in a let expression, we know it's being used. And if you have one of these features, well, that's not going to be a guarantee anymore. So it's really a trade-off, and I just want people to know, like, if you add a feature like this, it's going to be useful, but know what you're going to lose as well. So, to summarize, we've seen that missing information is the root cause of everything in static analysis. When you have missing information, you're going to make presumptions, and when they turn out to be wrong, you're going to have either false positives or false negatives. And that's going to be make your users frustrated, and they're going to distrust your tool. Maybe even your language, who knows? About guarantees, we've seen that when you have a parsing phase, you know that the syntax is correct. And compilers and type checkers are going to look for semantic errors, and they're going to remove a lot of surprises you would have when you analyze the code. And basically raise the number of guarantees that you can depend upon to make shortcuts and to make better analysis. If you don't have those tools, you're going to have communities are going to recreate those guarantees using a lot of linter rules. Those require, usually in the end, require pre-made or opinionated configurations. And when people adopt those, that's going to create false frustration because people don't agree with the rules that they've enabled. And when you have a pure functional language, that greatly simplifies different kinds of analysis. Like also, you don't have to check for mutation. Like if you don't have a mutation, you don't have to model your internal things in the analysis to worry about that. And that can lead you to have some very nice code simplifications that you would otherwise not be able to do reliably without any sort of risk. And that makes for some great dead code elimination. And all of that with a lot less false positives than you would have with side effects. Thank you very much.
Wow, perfect timing as well. You've got 5 minutes left for questions. That sounds like you chose a very good language to build a static analysis tool for.
Yeah, I didn't know.
The easy road.
Yeah.
You didn't know?
I didn't know, but I'm super happy.
Brilliant.
Because I think it's a great tool, but not because I made it great, a tiny bit, but it's just because it's a very easy language to analyze.
Nice.
Nice surprise.
Do we have no virtual questions at the moment, but please do type them in if you come up with something. Anyone in the audience?
So you mentioned that the vast majority of rules for JavaScript doesn't apply at all to Elm.
Yep.
And I wonder if you can think of some rule or warning that is specific to functional languages like Elm.
Yeah. So for instance, Elm has ADTs, algebraic data types, and you can in Elm review you have rules to say, well, these variants don't exist, or they're never used, so you can remove them. And you don't have that problem in JavaScript because you don't have ADTs. Maybe in TypeScript, kind of, but yeah. So it's like new opportunities to clean up. I don't know of anything that is really related to functional programming. It's like more new opportunities to remove code or simplify code that I can think of.
We use Elm Review at Superseed, and we think it's great, so thank you very much for an excellent tool. A couple of questions. Recognizing that the Elm compiler doesn't change much over time, which is fine, but do you expect any of the linting rules that you've come up with to be rolled into future versions of the Elm compiler? And then the second question is, do you have in mind any bits that are missing currently from Elm review?
Yeah. So for the first part, yes, I think there are some linting rules that could absolutely make sense as part of the compiler. So one example is that there's a rule that says if one of your expose function in a module returns or mentions a specific type that is in the same module, but that type is not exposed, then you have a problem that people who use that module can't annotate some values that use that function. And that can be a problem in some packages where they expose a function, but they actually they're not able to annotate or actually even use the function because some parts are not exposed as part of the module. So I think that could totally make sense in the compiler. So yeah. What was the second question again?
Are there any bits missing from Elm review?
Yeah, we don't have type information. That can be quite useful to do a lot more in-depth checks. Yeah, it's mostly like, as I said, missing information is a big part. And the tool is not giving all the available information to the rule authors. So we don't have type information. We don't know what the code is from dependencies. And I think all of those could be provided to the rule authors, and they could make the analysis much more powerful or precise. So going in that direction of removing missing information.
We have a question from someone online saying, does a podcaster help you as a developer?
No.
Sorry, does being a podcaster help you as a developer?
No. Well, maybe it helps my co-host. But the thing is, I have a pretty bad memory. So I don't remember much of what we say on the podcast. And because I don't like my accent in English, I tend not to re-listen to those podcasts. So I forget all the information that we've said on the podcast. It's useful for a lot of other people, but not to me.
Great.
And yeah.
I think we maybe have time for one more question. Anybody? Oh, thank you.
So I haven't used your tool. So is it opinionated about the style? So I don't know if you used HLint. For instance, it likes you to use point-free styles. It will say, oh, you should eta reduce this and put in point. Does your tool do those kind of things? Because that's kind of more matter of style rather than being an error.
Yeah. So no and yes. So actually, the tool, because it doesn't have any guarantees to give to the rule authors, like the compiler is already giving so much guarantees, the rule actually doesn't come with any built-in rules. Meaning that if you want to use any rules, you're going to have to find them on the package ecosystem from Elm. And therefore, there are not any opinions. The tool doesn't come with any opinions about how to write your code. And you're going to have to choose which rules you agree with, which is going to remove some frustration as well. There are some people who have written a rule to ETA reduce expressions. In practice, I tend to not like styling rules. I think that's an issue for code formatters, which we have a great one, which is called Elm format. And therefore, any styling issue that remains is like, doesn't really matter that much. Like, in practice,
There's one good thing about that. I've learned from things in HLint. It says, oh, you wrote this long thing. You could have written it in this short way instead with another function.
Yeah, so we do have a rule called simplify, which is just a lot and a lot of simplifications to your code that will teach you how to write better Elm code. But it's always going to be in the direction of simplifying the code, not depending on code style. So if there's some people prefer it written this way, some people prefer it this way, like ETA reduced or with a lambda, then I tend not to write a rule for that. But I tend to simplify what we can. Yeah.
Thank you very much. I'm sorry we're out of time.